So today we are going to review this paper named the Cauchy activation function and X. This was submitted in 28 September, so pretty recent paper. So what they claim in this paper is they claim to develop a novel activation function named the Cauchy activation function. This function is derived from the Cauchy integral theorem, which is used in complex analysis. And they are demonstrating that a neural network which uses this activation function instead of the traditional activation functions like ReLU and other similar activation functions like sigmoid, right? Instead of
Yeah.
that, if you use this Cauchy activation function, it performs very well. It learns fast, so the training happens. The learning during the training happens faster. Training accuracy is improved, and they are also comparing this with other approaches like, um, as I said, the ReLU activation function and the Kolmogorov neural networks. You remember
Yeah.
previously we talked about
Scan
this
network. Yeah.
CAN networks, which also created quite a buzz that they have better expressivity. Maybe they can have lesser number of neurons compared
Yeah.
to
Compared to
the MLP, right? So
right.
CAN was proposed as a better approach than the multi-layer perceptron or the MLP.
MLP.
Now, XNet claims to outperform both of them. So both CAN as well as MLP, they claim to outperform by simply changing this activation function. Okay. And they show that it is very effective in the MNIST problem. And then there is this fashion dataset, CFAR, in computer vision, and then this physics informed neural networks, and then even for solving partial differential equations. So, which is interesting, right? So, this is just the abstract. Okay. Now,
Right.
let's just glance through the paper, right? So,
Yeah.
the abstract we already read. So, what they are saying is, so this is the ReLU, just to recall, right? This is the ReLU activation function, right? This is the
Yeah.
sigmoid activation function, right?
Yes.
And normally what we do in a multi-layer perceptron is we have a linear layer followed by a non-linear layer, which is the activation function, right? So
Right.
we have linear activation function, then another linear layer activation function. So this is how we normally do things, right?
Yeah.
This is the simplest perceptron architecture I'm describing. Now, if you look at the Kolmogorov networks, which we discussed earlier, what they do is they remove all these linear layers, right? There's no matrix multiplication. Instead, it is simple addition operation, right?
Right. Yeah.
But then they have several one-dimensional learnable activation functions. So they take the
Yes.
input
Correct.
and apply this one-dimensional learnable activation function.
Right.
And then they add up all these outputs, and that essentially becomes one neuron's output. So like that, you can have multiple neurons, and that
Yeah.
is how the Kolmogorov neural network is built. So if you compare MLP against the CAN, MLP has linear functions which are learnable. So we have a matrix whose coefficients are all learnable,
Yes.
followed by an activation function which is not learnable, which is fixed.
It's a fixed function. Correct.
So there's either relu or sigmoid, or you have several other variants that people use. But the basic point is, it is a fixed activation function.
Yes.
In the CAN, we don't have the matrix. The matrix is gone, right? But the activation function is learnable,
Yeah, it's kind of the inverse.
right? So I'm just comparing the two, right? So in one case, we have the learnable parameters are the linear function in MLP, and then activation, the nonlinear component is fixed. In the CAN case, the linear part is not learnable. Linear part is just the addition. You're just doing this addition of the neuron outputs you're doing.
Yeah.
It's fixed. So linear part is fixed, but the activation function, the nonlinear part is learnable, completely learnable.
Learnable. Yeah.
And that's where we have many variants of the CAN, like B-spline CAN,
Yeah.
then wave-based CAN, then you have Chebi CAN, which is using Chebyshev polynomials. So basically approximating that activation function with various types of functions like polynomials or wavelets or spline functions. And those functions are parameters. They have parameters, and that is what you learn. So you learn the parameters of that activation function, right? And basically sum up the outputs of the neurons. So that is the CAN, right? Now CAN, the claim was CAN is more expressive, meaning it can represent very complex functions using fewer neurons because the activation functions are learnable.
Learnable.
So imagine I have a simple function like y is equal to sin x, right?
Yeah.
Now, if you have to approximate this y equal to sin x using the MLP, you're going to need multiple layers
Correct.
to approximate that function, right?
Right.
Whereas imagine if I can have a single activation function which is just sin x, right?
Yeah. Yeah.
You just pass the x as input, up the sign, and you got it, right? So
So can we say in that sin x, the learnable parameter in the case of CAN is the amplitude, let's say a sine 2 pi theta or phi plus theta, let's say phase and angle. These are the learnable parameters. Can we say like that in the case of this
kind
activation
of.
function?
So basically, depending on the problem,
Yeah.
see, depending on what function you are running, if you have the freedom to choose the activation function,
Yeah.
I can choose the most appropriate activation function for the particular problem, for the particular function I am trying to approximate. So this is
Got
definitely a better approach rather than having a fixed activation function. And then with MLP also you can approximate, but you're going to end up needing a lot of neurons.
lot of layers of neurons. Correct. Correct.
Lot of layers and lot of neurons will work. Eventually, it will approximate. But
Yeah.
how many parameters are needed to approximate? So that
Yeah.
is the difference.
Understood.
Now,
So the
this
universal approximation theorem states that any nonlinear function can be expressed using MLPs, right? So, but the question here is how many layers and how many neurons in each layer do we need to express the most complex functions? This is getting better in the case of CAN since the activation functions are learnable over there. So it is becoming easier. Can we? Okay.
yeah, you can say like that. But
Yeah.
the cans are not that trained
Hmm.
because the functions, the active functions themselves are non-linear. It was difficult to train them,
Hmm.
especially in high dimensions. Training cans is not that easy. So overall, if you look at it, um, CAN was not a clear winner as compared to the MLP. There are some cases where CAN may be better. There is many cases where MLP itself is better than CAN.
Mm.
When you look at it holistically, right? You look at how much time it takes to train, how complex it is to train, right? You consider all the aspects.
Yeah.
CAN has not yet emerged as a direct replacement of MLP, right? Still, even
Right.
today, we use MLPs.
Yeah.
Now, what this paper, the XNet paper, the Cauchy activation function, what they are proposing is a mix of both. So what they are saying is you have the regular matrix multiplications,
Mm.
right,
Yeah.
which is learnable. But instead of having a fixed activation function after the matrix multiplication, you have a Cauchy activation function, which has
Okay.
learnable parameters. So the
Got it.
Cauchy activation function is also learnable. So you
Learnable.
have both are learnable. The linear part is also learnable. The nonlinear part is also learnable. So the
Got it.
argument is this can potentially have better accuracy. Maybe it can train faster and all the. Maybe the expressivity is better. Maybe if your neurons are enough, right?
Yeah.
Because now the activation functions themselves are learnable. So the activation function that they are proposing is this function. This function has 3 parameters. Okay, so it's not like a lot of parameters. It's only 3 parameters. Okay, lambda 1, lambda 2, and d.
Okay.
And this is the function. So lambda 1, lambda 2, and d are the learnable parameters. So x is the input to the function.
Yeah.
Okay, so you can see here there is one component which is x by x squared plus d squared.
Mm.
Another component is 1 by x squared plus d squared.
Right.
And the lambda 1 and lambda 2 are basically weighting them differently.
Yeah.
Okay, and that's what this equation says. And if you look at it visually, this is how the Cauchy activation terms, the 2 terms, how they look. So they've separately plotted this one and this one. Okay.
Mm.
So term 1 is showing here, which is lambda 1 x by x squared plus d squared. And term 2 is 1 by x squared plus d squared.
Right.
I think for this plot, probably they assume lambda 1 and lambda 2 are 1. So you can see term 1 looks a shape like this.
Yeah.
The blue
It's kind of a sigmoid. Kind of a sigmoid, but not exactly sigmoid, right?
and then the other one,
Yeah. It looks like a sync function. I don't know.
it's basically 1 by x. See, x squared will look something like this U shape,
right.
right?
Correct.
Now
X
here
square
you have
will-
1 by x squared.
Yeah.
So you
Correct.
see
Correct.
inverse of that. you know, So basically, sum of these two, weighted sum of these two is the final function. Okay,
Mm.
and those weights are learned. So you learn those
Mm.
parameters. Okay. And, what happens if you change d? That also, I
Yeah.
think, probably it changes the width of this.
Correct.
I assume, if you change d, the width of this so-called, this function, it's like a lobe,
Yeah.
right? Main lobe.
Yeah.
That lobe width probably will
Okay.
increase
Mm.
or decrease. I think
Decrease. Mm.
similarly the term 1, this transition period, right? How long
Yeah.
it takes to transition
Right.
from the negative to the positive, right?
Yeah.
That I think it elongates or shrinks. I think that's how
Understood.
it plays. So you can see, it has some flexibility in there to represent quite a bit of functions. Okay.
Yeah.
Now, mathematically, this function has some special, properties. So there is this approximation theorem and that they are stating here, right? So basically, This is all. I think finally we can go to the theorem. This is the theorem 1, which is the Cauchy approximation theorem. Okay. So what they're saying is you have a function in n variables. Okay.
Yeah.
And that can be approximated, okay, by this kind of equation. Basically, summation k is equal to 1 lambda k by this
Epsilon.
yeah, psi 1 for k minus z1 and so on. So this kind of expression can approximate it to arbitrary accuracy. So this epsilon is basically telling how accurate you want it to be, and
Right.
depending on how accurate you want it to be, probably that there is a list of points, right? For k is equal to 1 to m. So the m might have to be adjusted. So more the m, it can have a better approximation. Right? So
Yeah.
this is for complex functions. Okay, so this function is on c power n, which is complex
Complex.
n-dimensional complex function. So obviously, you can real is a subset of complex. So therefore, you can do the same for real also. So for real, it can be simplified like this in this equation form. Okay, and for the one dimension case, okay, for one dimension case, you can simplify it like
Right.
okay. So basically, one variable function of one
Yeah.
variable,
Only one variable and okay.
you can put it like this. Okay, now so x here is real, but the zeta k and lambda k are complex. Okay, so from this, what they're saying is you can take the real and imaginary parts, okay, and then simplify it. Okay, by simplifying it, you can arrive at this function.
Got it.
So essentially, what they're saying is one-dimensional function. Okay,
Yeah.
a one-dimensional function can be approximated effectively by the Cauchy activation function. See, all the activation functions, the ReLU, sigmoid, they're all one-dimensional functions.
Yeah.
So this is a good approximation. Now, for some lambda 1, lambda 2, and d parameters, pretty much you can get a good approximation to one-dimensional functions. So therefore, all that you have to do is in a regular MLP, replace that ReLU or sigmoid with this function.
Function.
Okay. And they go on to provide a more general approximation theorem, because you have to again prove that, okay, when you put it in the MLP context, it can approximate any n-dimensional function, right? That universal approximation theorem, again, they are proving it again with the Cauchy activation function. So which is what they are doing here. And, proof is there in the appendix. We are not going to go over the proof. Now, we can look at the examples here. Okay, so first example is the MNIST. MNIST is the written digit recognition problem.
Correct. Yes.
So here, what they have done is they have used, the input is a 28 by 28 grayscale image. It is reshaped into a 184 by 1 vector. Then it is compressed by the input layer into n features, which are then fed to a n by n hidden layer. And then you have an output layer, which maps the n hidden outputs to 10 classes. So it's a simple, two-layer MLP. Okay, simple two-layer MLP. And they're comparing the ReLU activation function with the Cauchy activation function.
Okay, understood. So
And
this
here,
does not use any CNN, right? This use just a fully
yeah,
connected
fully
network.
connected network. Yes, no CNN, but you can use this all the CNN transformers. You can use the activate function wherever you want.
Got
So
it, got it.
basically, wherever you have a forward network, you can replace that activation function with the Cauchy.
Cauchy activation.
So that's what they are saying. So it's a drop-in, replacement. It's easy to do so.
Got it.
And what they are showing here, it's interesting, is if you see the training loss, right? The blue curve and the violet curve here, right? Sorry, the blue curve and the light blue curve. So the light blue is for the ReLU
Yeah,
and the dark blue is for the
mm,
Cauchy. Okay.
understood.
So
Mm.
let's look at the light blue. So the light blue has the training loss that
Yeah, it
declines.
takes longer. It takes longer, more number of epochs to reduce. The
But if you see
loss
that
takes longer.
blue, the loss steeply
Mm.
declines. you know.
Yeah,
Within 10 epoch, it has pretty much
yes.
got on even
And it
after.
gives better performance also compared to
So this is a
Renault.
law. If you look at the accuracy also, if you compare the light blue, this is
Mm.
the training accuracy,
Yeah,
and the for the dark blue Cauchy, it
yeah,
output.
yeah. This
So
is nice.
this is good, right? Now, like this, they are showing the benefits for various types of problems. This
Mm.
is with CNN with Relu. You asked, right?
Got it.
What
Mm.
about same
Yeah,
problem? Instead of MLP, they are using CNN with Relu and CNN with Cauchy.
Cauchy.
And here also, if you see this table here, they have summarized the results. You can see after 20 epochs, using a three-layer CNN, the training accuracy for Elu is 99.35, but Cauchy is a little bit higher.
Yeah,
Training
yeah.
loss also you see is lesser.
Mm.
So in all the parameters, right, it is doing well. And how fast it trains also is faster. It trains
Mm.
pretty quick, learns pretty quickly. Okay,
Yeah.
and same kind of observations with the CFAR data set, which is a different problem. There also they show benefits. Then in terms of solving partial differential equations also, they are showing that it does
Mm.
better. Now this is the first paper, right? But they have a follow-on paper where they show that it is better than CAN also.
Mm.
I think not sure if I downloaded that paper.
So one question on this, Prasinder. So can we also, reduce the number of layers or the number of, neurons per layer when we use this Cauchy activation function instead of ReLU or sigmoid?
Possible, right? See, one you can get better accuracy. So for the same number of parameters, he is showing better accuracy, which means for the same accuracy, you should be able to reduce the number of parameters. So
Mm.
it may be possible, but I haven't seen data that way. So this is a another paper where they say XNet outperforms CAN.
Mm.
So here they are comparing. So if you look at this paper, you can see results comparing CAN and the XNet.
Mm.
So I think what I like about this paper is CAN was like a completely different approach.
Yeah,
And it was difficult to train and so on.
correct. Yes.
Whereas here it's a small minor change in terms of code, right? If you look at the code change, it's
Yeah.
pretty small change. Instead of ReLU, you just use this new activation function and that's it. Right?
Yeah.
It's big to try, and I think the results are also very promising. And another thing I like about it is the number of parameters for that activation function is only three parameters.
Mm. Correct. Yeah.
Recall, you go back to the spline activation function in the CAN, it had many parameters.
Yes. Yes. Yes.
You remember there was degree of
Yeah.
polynomial.
Correct. The degree polynomial number
and
of
how
degree
points big
is
and so on, right? More points you pick, better the accuracy and so on.
yeah.
Here it's very simple. It's just three parameters, and I think it's a nice solution. And if the results are true, it is indeed, I think, uh, pretty impressive. So there is a GitHub repository I just came across
Okay.
for this XNet,
Mm,
where they have done for the MNIST problem with
mm,
the MLP. So MLP with ReLU compared against MLP with Cauchy activation function.
mm, mm. Yeah.
So this GitHub repository, shows all those code and the
Yeah. I
results,
think
right?
to also match the paper's claims, right, in terms of the
Right.
training
That's
loss.
what they show here. The results here match whatever the paper also claims. Now, what
Right.
I thought was, why don't we try to replicate this? Run it
Yeah.
and train it, and then see for ourselves
Right.
uh, the code and understand it a little bit,
Mm,
and convince ourselves, right? So I just copied over this code from the
mm.
GitHub repository.
Yeah.
Uh, can you see my screen actually?
Yeah.
Yeah.
Yeah. I can see.
So I just copied all the model related uh, code. I put it in one file. So
Mm,
it's a simple two classes. Okay. So
yeah.
one class is just defining what is that activation function. Okay.
Right.
Cauchy activation function. As you know, there are only three parameters. So there
Three
is
parameters.
lambda 2 and d, and they are all initialized with a value of 1. Okay. This is just the initial value. Okay. These are all learnable parameters. Okay. Then in the
Understood.
forward method, you have these two terms, right? That is
Yeah.
the 1 by x squared plus d squared, and the other
Yeah.
term was x by x squared plus.
Yes. Yes.
So that x squared plus d squared is what he's computing here.
Got it. Mm.
So x squared plus d squared is computed here. And then the final output is lambda times x by x squared plus d squared plus lambda 2 times lambda 2 by x squared plus d
Yeah.
squared.
Right.
This is straightforward, right? I guess
Got it.
this one is
Yes.
straight. Now
Yes.
he
Yes.
is incorporating this activation function inside the MLP. So his MLP, as he explained in the paper, right, that input is a 28 by 28. It's vectorized and brought into 784 dimensions. So he
Yeah.
has one input layer which takes 784 to 128 dimensions. Then he has one hidden layer which takes 128 to 128, and then a final output layer which takes 128 to 10.
Got it. Mm.
Okay. And in the forward method, so first line he's reshaping it to bring the two-dimensional
Yeah.
image to a one-dimensional vector.
Right.
Then he's applying the first layer, input layer. Then he is applying this activation function. Okay. Now the
Yeah.
activation function, he takes it as an input.
Right. Right. Mm.
This is coming as input. You can feed in either ReLU or
Yeah.
the Cauchy activation function. Okay.
Right.
So after input layer, you have activation function. Then you have hidden layer. Then you have activation function. Then finally the output layer.
Output. Right.
So that is returned. So this is straightforward, right? Any questions?
Yeah.
I guess this is
Yeah, I think
straightforward.
this is straightforward. But one thing to notice, the last layer, right after the output, there is no activation function at the end. I mean, he's so these are like probabilities, right? All the 10 outputs, right? They are probabilities, correct?
Yes,
So
yes.
whichever value, yeah, okay. So there is no need for activation function at the end, or is there any specific reason? Because we typically use some sort of activation function at the end, right?
So if you want, you can have it. Usually
I
they
see.
don't. Because anyway, you will compare against the output, right?
Yeah.
So you have a labeled data set, right? So if the label is like
Right.
within 0 to 1, it is going to try to make the output layers output also within 0 to 1,
Yeah.
right?
Got it.
So
Okay.
you don't have to put the sigmoid and force it. If you want, you can put it, but it's not,
Yeah.
really, necessary. Now let's look at the training code. Right? So training code, um, there is this train function and test function. So train function, let's quickly go over it. All that he's doing is he's taking the data from a data set loader, right? Okay, train loader. And then he's getting the data and the target, feeding it to the device. Then the optimizer is initializing it with the zero gradients, and then he's computing the output. Then loss is computed, right? So that criterion, okay, what is the criterion? We'll have to see what criterion is using, and then back propagation. And I guess this is standard, right? Standard training. Same thing for the next data set. Okay.
Yes.
Now, device is CUDA if it's available, and then he's taking the data set from MNIST. So, and it is downloaded from the internet. Okay. So from here, he gets a train data set and the validation data set. Okay.
Yeah.
Here he's entering train as false, so that's how he gets validation.
Yeah.
Then train loader, he is having a batch size of 64. For validation, he's using a batch size of 1000. Okay.
Okay.
And this is shuffled.
Shuffled. Training loader is shuffled. The other one is not shuffled.
Now he is defining two different neural networks. One is the MLP with ReLU. So here he is initializing neural network that he's calling the neural network class, which we define, and he's specifying the activation function as nn.relu.
Right.
Okay. Then other XNet, there he's defining the activation function as Cauchy activation, and that is instantiated here. So he's creating a Cauchy activation instance, and that he's passing to as the activation function to the neural network. So there are two different neural networks. So he's going to train both these neural networks on the same data and then see what's the result. Now, the criterion he's using is a cross entropy loss because this is a multi-class classification problem. So there are 10 different classes, 0 to 9, right? The digit 0 to 9. So he's using a cross entropy loss. So this criterion is what is getting used here, you know.
Yeah.
So this is the cross entropy loss. Then optimizer uses Adam optimizer, which is a standard. And I guess the rest of the stuff is standard. So here is your training loop. So first he is training the ReLU model. He's running over 20 epochs. Okay. And then he is tracking the training loss and the training accuracy and the validation loss and validation accuracy in an array. So he's just up and down these arrays so that later on he can plot the results and see. So after that, he's training the XNet, same things, and then he's plotting the results. So I guess it's a straightforward code, right?
Yeah.
So we can run this now, and then we can see how the results look. Okay. So I'm going to run it. So it started training now. So this is running on my local GPU.
Okay.
Which is a 2080 Ti. Not a great GPU, but that's all I have. So you can see here, right? So it's now training the ReLU, right? So let's just see now, like to get 98% accuracy, how many epochs you need.
Yeah.
So it's training accuracy is 92, 93. Let's see when it starts hitting 98. The learning has become slowed down a little bit. Initially
Initially it was faster.
Then after
Now
it crossed 94, it's been like very slow. Like the accuracy improvements are going slow.
0.2% now every time. 0.3, 0.2, now 0.04%. A bit better.
Compared to CAN, right? I think it's very easy to duplicate this.
Yeah.
Because CAN, I tried myself. It wasn't that straightforward to train on a MNIST or CPAR or any of this well-known
Correct.
data. But I'm hoping XNet will be easy. It's almost going to complete 20 epochs.
Yeah.
So it reached 98% training accuracy exactly at the 20th epoch
Yeah.
on the training data set. No, I won't give much importance to the validation accuracy here. The
Right.
reason
Right.
is in this code, he has not
Mm.
taken any measures to address the generalization error.
Which
Not
error? Which error? Come again, Susinda.
no, there is this training loss, and then to
Mm.
improve the validation loss, right? You
Yeah.
have to take some measures. There are
Mm-hmm.
some strategies to do generalization, like how well your model generalizes to data, unseen data,
Yeah.
right? You have to do some measures, and he has not done anything in this code. So typically, right, you will use strategies like dropout, um, or you will do a L2. You will add a L2 loss function
Yeah.
to the cross entropy loss. You will add one more parameter there.
Yeah.
Okay, and that will be like norm of all the weights, so that
Mm.
the neural network tries to have a smaller set of non-zero weights. So he
I
has not taken any steps. So I won't look much into the validation.
validation accuracy.
Yeah, I think we just focus on the training accuracy. So let's look at the extent is already running, by the way. And in terms of the speed of training,
Yeah.
I don't see much of a big difference, right?
Yeah.
And you see here, it's already like 98 in the
Yeah.
seventh
Correct. Seventh epoch. Yeah.
epoch itself. It reached.
Yeah. It is going even beyond. I think its training accuracy is getting even better. It's already 99.7, now 99.8.
Yeah, it's pretty good. Now, to be fair, right? It's not the same number of parameters, right?
Yes.
See,
Yes.
if you look at this right now in the ReLU case, the activation function is fixed. So how many parameters you have? You have
Mm.
74 by 128
Yeah.
plus 128 by 128 plus
Yes.
128 by 10, right?
Correct.
Then there are these bias parameters. Uh,
Mm.
you know, let's say we forget it, right?
Mm.
Those are the learnable parameters in the ReLU case,
Mm.
right? But in the Cauchy case, you have these parameters plus 3 parameters for every activation function.
Mm. Right.
So I guess he's using the same activation function in both places. So it's basically 3 parameters in addition.
Only three parameters, right? Totally only three parameters.
So totally he's adding a 3 more parameters.
Yeah.
Ideally he could have used
Two
activation function.
different activation function. Activation function 1 and 2.
So then he could have different lambda 1, lambda 2, and D
Correct.
for the
Correct. Correct.
two.
Exactly.
Maybe he can do even better. But I think he kept it simple. So it's only 3 parameters. Now here is the plot actually
Mm.
where we can see the training loss comparison and the training
Yeah.
accuracy comparison. So, within 10 epochs, it's already reached,
Yeah.
98
Correct.
loss. Also, you can see clearly, the
Yeah.
graph speaks for itself. Now, validation, as I said, worse here.
Mm.
The ReLU does a little better, but as I said, it's not a fair comparison because you should
Mm.
get some measures for improving the validation accuracy, and nothing has been done. So either you should add a dropout layer, or you should have added a L2 loss term. Then
Right.
results may have been different. So I wouldn't read much into this portion, but this is
Yeah.
pretty
Yeah.
impressive.
This correct. Correct. I think this is really good.
Yeah, so that's all I wanted to share for today.